Good morning everyone. In today's video lecture, we discuss about different types of transistor biasing circuits. We have various biasing circuits that are available to bias a transistor. Those are fixed bias circuit, fixed bias with emitter resistor, collector to base bias circuit, which is also called as collector feedback bias circuit, and potential divider bias circuit, that is a voltage divider bias circuit. Out of which, in today's discussion, we will have a conversation about collector to feedback bias circuit. So why do we call this as collector feedback bias circuit is, the reason behind that is, between the collector terminal of a transistor and the base terminal of a transistor, there is a feedback resistor which is being connected, and that is actually the base resistance RB. That's why it is called as collector feedback bias circuit. And this particular configuration employs a negative feedback, which is mainly for preventing the thermal runaway and also to stabilize the operating point. So in this form of biasing, the base resistor is connected to the collector instead of connecting to the DC source. We have not connected that directly to the DC source, since because of that reason it is directly connected to the collector's terminal. Okay, and so that is the reason why the thermal runaway will induce a voltage drop across the collector resistor that will throttle the transistor's base current. Okay, and then this collector to base bias, that is collector feedback bias circuit, is having the configuration in this fashion, that is resistor, that is collector resistor, base resistance, via which the base current flows through the transistor, and the collector current which flows over here, and the emitter current is actually emitter terminal is being grounded, since it is a common emitter configuration. So from this we can write the expression that VCC equivalent to IC plus IB into RC plus IB into RB plus VB, that is voltage drop across the base and the voltage drop across the base and the emitter terminal, that is VBE, voltage across VBE. So this particular region is considered to be VBE, and from this we can calculate the value of base current, which is nothing but IB equal to VCC minus VBE divided by 1 plus HFE into RC plus RB. So from this, the operating point can be considered to be as ICQ, that is collector current is nothing but HFE into IB. So that is ICQ is nothing but Q point. And similarly for VCEQ, from VCE we can write the term as VCEQ. So VCEQ can be written as VCC minus HFE plus 1 into IB plus VCC minus what? VCC minus HFE plus 1 into IBRC. So from this equation we can write approximately the value of VCEQ as VCC minus ICQ into RC. And coming to the stability of the collector feedback bias circuit, first the value of HFE increases, which in turn increasing the value of IC, that is IC increases, so that if IB is same, then value of VC decreases, which in turn decreasing the value of IB, and the value of IC does not increase that much. The value of IC does not increasing that much, so which represents good stability, and which is lessly depending on the value of HFE and temperature, which is lessly depending on the value of HFE and temperature as well. And the collector feedback characteristics. The collector feedback characteristics having the recognition that the base resistor is connected between the same as we discussed between base and collector terminals of the transistor, and its advantage is considered to be it's a very simple circuit and it is relatively stabilizing the Q point. And major disadvantage of this collector feedback characteristics is its relatively poor AC characteristics, and it's one of the important application is it can be used in bias linear amplifiers. It is primarily used for the bias linear amplifier circuits. And now we will have to apply the Kirchhoff's voltage law to the base circuit for writing the expression that IB plus IC into RC plus IB into RB plus BBE from the collector to base bias circuit, which is can be differentiated with respect to the value that dou IB by dou IC equal to minus RC divided by RB plus RC. Therefore, from this, the stability factor can be written as 1 plus beta divided by 1 plus beta into RC divided by RC plus RB, where the value of 1 plus beta, which is less than value of 1 plus beta, signifying the better thermal stability. This particular equation will be less than the value of 1 plus beta. And then major some important points that will be highlighted from all the different types of configurations is the Q point is the best point for the operation of a transistor for the given collector current. The purpose of biasing is to establish a stable operating point. The linear region of a transistor is the region of operation within the saturation and cutoff region. Out of all the biasing circuits, the potential divider bias circuit provides highest stability to the operating point. Thank you. Rest we will continue in the next video.